Okay, so welcome back to Algebra 2. Today's lesson is the number e and the natural logarithm. So just at the point that you think you know all the numbers, you've got the whole numbers, you have the natural numbers, you have the integers, you have the rationals and the irrationals all making up the real numbers. But then beyond the real numbers, we have I, which we haven't really talked about yet, at least I don't think so, and then pi. Well, pi, you worked with pi a lot last year in geometry. Pi is simply the ratio between a circle's circumference and its diameter, which stays constant at 3.1415926, blah, blah, blah. All right, so now we're going to talk about the number e. So instead of me telling you about it, I found this cute little video that talks about it. So why don't we take a look at this?
We've made a video about pi, the ratio of a circle's circumference to its diameter. But there's a less famous, but equally fundamental number known to anyone who's taken high school algebra. It's about 2.718281828459045, and so on. And it was first defined by Jacob Bernoulli, but later Leonard Euler called it E, and the name stuck. Bernoulli first defined E through compound interest. Now, compound interest says that you get a little bit of money in interest every period, and that money you gained helps you gain even more interest next period. In other words, your interest compounds. So, if you stick $1 into a bank account with 100% interest rate compounded annually, you'll get $2 at the end of a year. If it's compounded semi-annually, you'll end up with $2.25. Quarterly, and you'll end up with $2.44. Monthly, $2.61. Weekly, $2.69. See where we're going? If you increase the number of compounding periods a year towards infinity, then you'll get closer and closer to E dollars. In statistics, it describes the most important statistical distribution, the normal. In biology, it models populations of species through the logistic function. In physics, E describes the exponential decay of a radioactive material. So, while E may not be as famous as pi, it's easily as fundamental and immensely important.
Okay, so that was just a quick synopsis of what the number e is. Now, we're not going to use it for some of those crazy things that they talked about in statistics and in science, although you can talk to your science teachers about how it is used for looking at decay and looking at population of bacteria and things like that. But we are going to use it a little bit here, but you'll see that some of this is beyond the scope of our course, and we're just going to use it based on one easy formula. So don't flip out. It's only one lesson. We could make an entire course out of this number, but we're just going to talk about it for one lesson, okay? And it has to do with logarithms, so we're going to just pull in how that is relevant. All right, so like pi, e is irrational. The number e is approximately 2.72. Like pi, which is 3.14159, blah, 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 blah. E is also irrational. It's 2.712818284590, blah, blah, blah. All right, so it goes on forever. So we just basically, like we say, we're going to use e on our calculator whenever we're calculating with it, just like we use pi in our calculator. We never ever use its approximation. All right, so just taking a look at exercise 1, which of the graphs below shows y equals e to the x? Explain your choice and check on your calculator. Well, you can't check on your calculator because I have your calculators here. But explain your choice. So can you tell me what this would look like? Without your calculator, you should be able to tell me that this is an exponential function, because if we think about this being y equals 2.72 raised to the x power, I know this is an exponential function, so I know that it's not going to be the quadratic here, and it's not going to be the cubic over here. It's going to be one of the exponentials in the middle, but is it increasing or is it decreasing? So you know your base is greater than 1, so I'm hoping you realize that this has to be an increasing exponential function. All right, so take a minute, pause this, and just write down a little bit about what we just talked about. The fact that the base is greater than 1, we know this is an increasing exponential function. Okay, so very often E is involved in exponential modeling of both increasing and decreasing quantities. The creation of these models is beyond the scope of the course, which I was just saying, but we can still work with them. All right, so let's take a look. Exercise 2. Notice how in exercise 2 it talks about the population of llamas on a tropical island can be modeled by the equation. So if you see they give us the equation, we don't have to come up with it, although we are going to use this formula a little bit later, where T represents the number of years since the llamas were first introduced to the island. So how many llamas were initially introduced at T equals 0? Show the calculation that leads to your answer. So we're going to start with our P equals 500 e to the 0.035 t. So when t is equal to 0, my entire exponent goes to 0. So we get p is equal to 500 e to the e to the 0 power, because 0.035 times 0 is 0. And anything to the 0 power, pi, e, 5, 12, negative 14, anything raised to the 0 power is always 1. So I know that p has to be 500. So this is my initial. So this works very similar to our example before. So we know that our a, because remember, this is like y equals ab to the x. So in this case, our a is 500, our b is e, and our x turns out to be our time exponent. So algebraically determine the number of years for the population to reach 600. So what we're doing there is 600 now becomes my population. And we're going to use the same formula, e to the 0.035 t. All right, now, there's not a lot of room here, so my apologies. You might want to watch this first and then try to write it down. Actually, I'll even tell you, why don't I'm going to move this over just a little bit. So the first thing we do is just like before. I'm going to work with it on the right-hand side just because I don't have that much room here. So I'm going to divide both sides by 500. And I'm just going to count this as 6 over 5. So now I'll rewrite it as e to the 0.035 t is equal to 6 over 5. So now what we're going to do is we're going to log both sides. So we're going to say 0.035 t log e is equal to log 6 over 5. All right, so 0.035 t is equal to log 6 over 5 divided by log of e. We're going to put this whole thing in our calculator, and then we're going to divide it by our 0.35, and t turns out to be 5.2 years. It says around to the nearest tenth. Okay. So we solve this very similarly to the way we just solved the last one. But instead of saying log of 1.2 or 1.9 or 7, we have log of e. And we find our e on the bottom of our calculator left-hand side where the pi sign is. So we'll talk about that in class when, actually I can show you here, hold on. Okay, here's our calculator. So if you look on the bottom left, you'll see the parentheses, you'll see a double E, and then you see this pi. So when you open up that pi, okay, mine's having a little bit of a conniption attack here, but when you open up that pi, you'll see pi, I, infinity, E, all right? So the only ones we're going to use here during our course is we're going to be using pi, I, and E. So here's our E right here. And when we put E here, I think if you enter it, you will get the 2.7. But if you did something like times 2, you'll see how it comes up with much more of it. It actually will use the actual example of E, the actual number of E, and it does not round it, which is very cool. All right, so let's go back to our lesson. So because of the importance of y equals x to the e, its inverse is known as the natural logarithm. It's also very important. All right, so this, when you write down y equals, and I say ln of x, I don't say natural log of x, I usually say ln of x, but what this means, and this is right here, What it means is it's base e, all right? So y equals log base e of x. And the beautiful thing about this is, and for you guys, is the only time we use this is then when we're using e. We do not use this any other time. So a lot of people say, well, how do I know whether to log it or to ln it? And I said, well, does your original exponential equation have an e in it? And if the answer is no, then we use logs. We don't use ln. We don't use natural logs. Okay, so this is the last new log that we learned. All right, so we learned regular logs, we talked about the common log, and now natural logs. All right, let's go on to another example. So the natural logarithm, like all logarithms, gives the exponent as its output. In fact, it gives the power that we must raise e to in order to get the input. So without using your calculator, determine the values of each of the following. So ln of e. So let's just start. I mean, not that you need to do this, but again, I always feel like it's important to try to translate just to see what's happening. So what does this mean? Let's translate it. This means log base e of e, which means my base raised to what power is equal to the answer, which is e? Well, obviously 1. So this is one of the most important calculations that we are going to use in this lesson. Okay, so now how about the ln of 1? So what this means is log base e of 1. So this means e, my base e, raised to what power is 1? Well, we know anything to the 0 power is equal to 1. And these are just the exponent. You know that a logarithm is an exponent. So here the answer is 5. Here the answer is a half, because that's what the exponent is. If you want to take a minute and say this means log base e of e to the 5th, means e to the what power is equal e to the 5th? Well, 5. Do the same thing for d. Log base e of, let's rewrite square root of e to 1 half. So it means e to the what power is equal to e to the 1 half, and it's 1 half. All right, so when I rewrite this, this is how I translate it into regular logarithms, because that's what that ln of e stands for. Why they created a whole different notation for it, I don't know. I just think it's because some people flip between logarithms and natural logs so often, it just makes sense to use a different notation for it. Okay, so when we take a look at exercise 4, we're going to use the same laws that we've been doing before. Sorry, had a quick interruption there. So exercise 4, which of the following is equivalent to the ln of x to the third over e squared? So we're just going to apply the same rules that we just worked on. So this means this is the same thing as ln of x to the third minus ln e squared. Pull the exponent out front. So 3 ln x minus 2 ln e. Now, this is what I was just telling you, that the ln of e is one of those really important numbers that we will always know, because the ln of e is equal to 1. So this becomes 3 ln x minus 2. All right, look at exercise 5. When you look at exercise 5, it's a little scary, because you look at this and you think to yourself, wow, this just look at what this looks like. It looks like something that's out of a rocket science magazine. But anyway, a hot liquid is cooling. Oh, see, this is the introduction of what's called Newton's law of cooling. We're going to do an entire lesson on this later on in this unit, but a hot liquid is cooling in a room whose temperature is constant. Its temperature can be modeled using the exponential function shown below. The temperature T in degrees Fahrenheit is a function of the number of minutes m. So basically what that means, and I think you know this already, the Fahrenheit is a function of the number of minutes, which means this here, T of m. All right, so don't flip out when you hear things like that. So what is the initial temperature of the water at m equals 0? It says do not use your calculator. You don't have your calculator with you, but beware here because that plus 67 is a little bit different than our usual model. So let's think about what that math looks like. So when m is equal to 0, I get t of 0 is equal to 101 e to the, well, negative 0.03 times 0 is 0, all right, plus 67. So my initial temperature is 101 times 1 plus 67, which is 168. So there's my T of 0. So as you can see, when you have something with a plus 67 on it, think about what happens on a graph. All right, so what happens on a graph is you have an exponential function that might look something like this. All right, and when you have a plus 67, what that does is it takes your y-intercept, and whatever that is, in this case our y-intercept would be 101, but because we shifted up 67, it ends all the way up here at 168. All right, so just try to give you a little bit of a visual of what's happening on a graph. So B says, how do you interpret the statement T of 60 equals 83.7? Well, remember what the M stands for in the T of M. So this is my M right here. So what this means is after 60 minutes, because that's what that stands for, the temperature of the liquid is 83.7 degrees Fahrenheit. So when it tells you to interpret, it means it wants to know what's going on in the context of the problem. All right? So now C says using the natural logarithm. I'm going to remind you, it won't tell you that. That part will probably be missing. It'll say determine algebraically when the temperature of the liquid will reach 100 degrees Fahrenheit. Show the steps in your solution. So hopefully you've done writing all this down. If not, pause it before I move up. All right, so you have it in front of you. I have it in front of me. So let's do something here. So we know that 100 degrees. So I know 100 is equal to 101 e raised to the negative 0.03 m plus 67. And we need to solve this for m. So we need to isolate the m. So in other words, this part right here needs to be by itself. So we're going to minus out 67 from both sides. And if you don't mind, I'm going to rewrite it as 101 e to the negative 0.03 m is equal to 33. Now we know to bring that exponent down, we have to log, but because we have e here, we're going to natural log. So what I mean by that is I'm going to kick this out front first, and I'm going to say ln of e wait. We have to do something first. I have that 101 there. Sorry about that, guys. I'm not paying attention. I need that e by itself. Divide both sides by 101. So now we have e to the negative 0.03 m is equal to 33 over 101. Okay, now this makes sense. So now you natural log both sides. So negative 0.03 m, kick it out front, ln of e is equal to the ln of 33 over 101. Divide both sides. Now we know ln of e is equal to, we know that this is equal to 1. So we're going to end up with divide by negative 0.03. And m turns out to be 37.28. This is rounded to the nearest tenth, so m is equal to 37.3. Notice when I'm done, I mean, I think you guys are mimicking this a little bit, but you come up with different numbers, m here. Notice when I'm done and I have the actual answer that I want to make clear to who's ever looking at this, I put it in a box, all right? So make sure that you're paying attention to that. All right, so let's take a look at the letter D. On average, how many degrees are lost per minute over the interval? So even if you didn't know what this was asking, think back to what we've done so far. That gives us intervals, because sometimes we are a little confused about what they want us to do. So if they're giving me an interval and it says on average, how many degrees? So hopefully you're feeling that average is the average rate of change. So interval means x values. So in this case, our x value, so we're going to have 10 comma something, and we're going to have 30 comma something. And what I do is I put my 10 into the original problem, and I come up with my y's. So if you don't mind, I'm not going to do that here. 141.8 and 108.1. Another way that you can do this is you can put this into your calculator. So you can take, let me just go for a second here. You can take this whole T of M, change your M to an X, and you can put this whole thing into your calculator and look at your table. Because at your table, it'll say 141.8 when X is 10. It'll say 108.1 when X is 30. So there's a couple of different ways to come up with your Y values. And now we're simply going to do the average rate of change. So we're going to do, oh, let's go this way, keep it positive. 140, what's going to be negative anyway? 141.8 minus 108.1 over 10 minus 30. My answer does come out to be negative 1.7, but remember what that means. It means it's losing it. So make sure that you say it loses 1.7 degrees between 10 seconds, 10 seconds, 10 minutes, I'm sorry, 10 minutes, 10 minutes, and 30 minutes. Please write the words out on a Regents exam. Here I'm just doing it fast. You can use shorthand here, but on a test, on a Regents exam, don't write in shorthand. Don't truncate the words. All right? So this one went a little bit beyond our 20 minutes, which makes me sad, but I'll get over it. Hopefully you do too. So natural logs, pretty cool. We're going to be doing a little bit more with this, but not a lot. So we're going to be talking about compound interest. They talked about compound interest in that little video we looked at. So the next lesson we're going to talk about is compound interest, which is very cool. And then we're going to also look at some more examples of Newton's law of cooling. So until next time, make good choices. Bye-bye.